Welcome to this video, which is going through task 3 of unit 1 of materials. So let's have a look at what this video is going to be about. So we're talking about the ideas of the shape of stress strain graphs and how to calculate the Young's modulus of a material. So let's get straight stuck into the task of explaining everything. So we've got the idea of drawing a stress strain graph, labelling the following points: limit, proportionality, elastic limit and the yield point. And we need to include a definition of each of these. Okay, so let's have a look at this graph over here. I'll just move the webcam out of the way. So you can see that from this graph, okay, we've got a stress strain graph here that curves, okay. We've got the limit of proportionality here. So up to this point, stress is directly proportional to strain, or Hooke's law is obeyed. So the whole of this is known as the linear region, and for that entire time, extension is directly proportional to force. In other words, Hooke's law is obeyed, and the point at which this behaviour stops is called a proportionality limit, or the limit of proportionality. So that's that point there. So at this point, extension is no longer proportional to force. Just beyond that, we have something called the elastic limit. And at that point, things no longer behave elastically. So remember, elastic deformation is where things return to their original shape. Plastic deformation is where it no longer returns to its original shape. So beyond this, it no longer behaves elastically and it starts to behave plastically. Beyond the elastic limit is the idea of the yield point. So at the yield point, the whole material yields. In other words, what we mean is that when you're applying a force to this, it actually starts to stretch quite quickly beyond this. So think about a strawberry lace to begin with as you're pulling it. It will sort of return to its original shape, but then when you apply a large enough stress, it will actually go to a point where it will not return to its original shape, and it's actually quite easy to separate. It's the point at which a large increase in strain is shown for a small increase in stress. So a small increase in stress, but a large increase in strain. So there are 3 main points that we need to talk about. Remember, if there's plastic deformation, or there's a plastic region, the extension is rapid for small increases in force. So anything that does that is ductile. So this is the shape of a ductile graph, essentially. Okay, right. Let's get back to the ISP. So we've gone through each of those words there with definitions for each of those. So that's the graph to use to help you do that. So remember, that is in your book towards the end of the pages listed at the top of the ISP. Explain the difference between elastic and plastic deformation. Include graphs to help. So remember, the graph above can actually help you through that. Elastic deformation is where it returns to its original shape once the force is removed. Plastic deformation is that it remains deformed once the force has actually been removed. Okay, so if it's elastic, it's going to return. Plastic, it'll either snap over here, so it will go up and the line will come down, say like for brittle, that's plastic deformation, or it will continue to have this long line where it deforms and will not return to its original shape. It's a nice, straightforward explaining everything. So let's get stuck into the questions. Okay, here we go. So force extension graph for thin copper wire is drawn. So you get thin copper wire. Show clearly on the graph the region at which copper wire obeys Hooke's law. So just over here, you can circle it, or you can do a little curly bracket to show that it's this area over here where force is proportional to extension, where it looks like a straight line through the origin. That's where it obeys Hooke's law. What additional information would you need in order to calculate the Young's modulus for copper from this graph? Remember, Young's modulus. Excuse me, sorry, I was just taking a drink. Young's modulus is given a symbol epsilon. Okay, Young's modulus is given a symbol epsilon and is equal to stress over strain. Okay, I'm just trying to remember the symbol for strain right now. Let's see if I've got it in the. I think I'll use one of my symbols incorrectly. Let's see if I've got it in the back of the ISP or somewhere there. Oh, I know it'll be in the other ISP. Oh no, here we go. This is the bit I was after. Materials, stress and strain. Yeah, strain is just the small one. So yeah, apologies. That's the capital E. Young's modulus is the capital E. Stress over strain. So the epsilon underneath over here. So stress over strain. Sorry, wrong video. Oh, sorry, wrong file. I mean, back to over here. There we go. So what additional information we need to calculate Young's modulus? Well, we could figure out the stress, because stress is just force over area, but we cannot figure out the strain, because strain is a length over, sorry, we can figure out the strain because it's extension over original length. You can figure out the original length. Well, no, you can't actually, because they haven't given you that, and they haven't given you the cross-sectional area. So technically, what you need is the original length. I think it's right around. It's extension over original length. So we haven't been given the original length, and we haven't actually been given the area as well. So cross-sectional area and original length. Estimate the energy stored in the wire when it's extended to 20 millimeters. So you go up from 20 millimeters, and you need to estimate the area under the graph. So take it as a big triangle, and then figure out what that rectangle is over there, and that tells you the energy stored inside of it. So that's question 7. Question 8. A wire fence is made from steel of diameter 2.5 millimeters. As soon as I see that 2.5 millimeters, I convert that to radius, because I know I'm going to have to figure out cross-sectional area. So that's 1.25 times 10 to the minus 3. So I've also converted it into meters, and I might as well figure out the cross-sectional area. And you can see the question is actually asking for cross-sectional area. So area is equal to pi r squared. So it's pi times 1.25 times 10 to the minus 3. So just that part of it is squared, just the radius. And let's type that through and see what we get. Apologies if you can hear my washing machine spinning in the background. Sorry, just get the calculator back in shot. 1.5 minus 3 squared. Okay, so I would put a minus in. Such a large value. Okay, and there you go. So it's about 5 times 10 to the minus 6, which is exactly what they wanted. Spot on the money. Excellent. So it's at 4.9 times 10 to the minus 6 meters squared. Right. So force now of 1,500 newtons is applied to the tension at a single length of wire. Calculate the stress produced in this wire. Okay, so stress, as we know from our equation list, so flick back to the equation list if you need to. Stress is force over area. Okay, so stress is equal to force over area. So we've got a force of 1,500 newtons divided by an area of 5 times 10 to the minus 6. It's pretty straightforward. Okay, so it's a huge value, and that's correct. It's got a small, because we've got a very, very small area, so we have a very, very large stress. Okay, so it's 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 3 times 10 to the 8. Speed of light, value for the speed of light, or whatever value for the speed of light rounds to. So that's going to be newtons per meter squared. Now, Newton per meter squared is also the same as a Pascal. For those of you that that I don't teach, there's a horrible joke that helps you remember that. For those of you that I do teach, remember the horrible joke. So there we go in terms of our stress for this wire. Now it's asking us to calculate the Young's modulus in millimeters produced at 33 millimeter in a 33 meter length wire when it has been tensioned. Okay. So they want the extension, and we've got the Young's modulus. Okay, so we've got Young's modulus is 210 gigapascals. Gigapascals, or giganewton per meter squared. We've got our original length of 33. We know our stress, which is 3 times 10 to the 8. So we just want extension is equal to question mark. Okay, so from before, just lay that all out so you can see it. There you go. So from before, we know that that is equal to stress over strain. So Young's modulus is equal to stress over strain, which is equal to, well, we've got the value of stress, so we don't need to write force over area for that. But this is equal to extension over original length. So let's rearrange this whole expression. So let's swap these two bits over because they can swap directly. So extension over original length is equal to stress over Young's modulus. Straightforward so far. We know the values of each of those. So this side, this is being divided. On this side, we're going to multiply through by that. So we need to multiply that by the original length. So we need to multiply the strain by the original length, stress, sorry, by the original length, and then divide by the Young's modulus. So our values, I'll just move across slightly so we can see it. Our values are going to be 3 times 10 to the 8 times by 33 divided by our Young's modulus, which is 2 times 10, so 210 times 10 to the 9, because it's gigapascals. So 3 times 28 times by 33 divided, oops, let's run this through properly, divided by 210 gigapascals, so times 10 to the 9. So we've got an extension of 0.05, if we round that up, 0.05 millimeters. 0.05, sorry, 0.05 meters. So that's 5 centimeter extension. Okay, so let's check all our marks for questions 8. There we go. So, yeah, we use the exact method. Okay, it's exactly what we did. Yeah, we got 3 times 10 to the 8. We got about 40 millimeters. 48 millimeters. Yeah, which is exactly what they got. Brilliant. Okay, so about 5 centimeters. We said 48 millimeters. Perfect. Okay, let's scroll back to the top of this. Right, question 9. Let's move this out of the way over it. Is asking about Anglo-Saxon gold shoulder strap. It's been excavated. Okay, there's got a description of the clasp. It's made by hammering gold, fixing thin gold wires to make cloisons, which are like compartments. It's heating to bind the paste to gold, forming a hard, shiny, attractive layer. Gold was used to make the clasp because it has suitable properties. Fill in the gaps below to name the 2 properties described below. So, gold can be hammered into shape to form its basic shape. So that means that it's malleable. If it can be hammered into shape, that's malleable. Gold can be made into thin wires. That means it's ductile. Ductile is drawn into wires. Malleable means it can be hammered into shape. So we should know that from the GCSE. So when wire is stretched, the load extension graph would have a typical shape shown below. Okay, so that's force against extension, has that shape there. The graph can be divided into 2 regions, A and B. Name the property exhibited in A, so that's elastic behaviour. It will return to its original length, obeys Hooke's law there. What is meant by the terms hard and plastic behaviour? So we know what plastic behaviour means. It does not return to its original length once the force is removed. Hard means it's difficult to scratch, difficult to scratch is the idea. Draw a labelled diagram of the apparatus you would use to determine the Young's modulus of copper wire. Copper in the form of wire. Okay, so it's pretty straightforward in terms of the equipment you actually need. Let's just check how many marks this actually is. Okay, so it's only 3 marks. Okay, so the equipment you actually need to find a Young's modulus of a wire. Okay, you need a pulley. You need a wire that comes over the pulley. You need mass hangers to apply the force. Okay, let's attach this all to a table. Okay, you need a block of wood and a G-clamp and another block of wood on top to hold the wire in place. You need a ruler to measure extension. You need a micrometer to measure cross-sectional area. So remember, if you figure out the Young's modulus, you need force over area. So to figure out force over area, you need to do, as you were saying on the previous slide, you're not force over area, stress over strain to figure out Young's modulus. Apologies for that. Stress over strain. So this will be force over area divided by extension over original length. So you need masses to apply the force. So you get to times that by 9.81, essentially to figure out the value of the force. So if it's 100 gram masses, times by 9.81, which is the size of the force. 100 gram masses. So that's 0.1 kilograms. So you get the masses into kilograms times by 9.81. That tells you the size of the force. The cross-sectional area will be figured out from the diameter by using the micrometer. The extension will be measured using the ruler. The original length will be measured using the ruler. Suggestion: appropriate length of wire to be tested. Generally anything over 2 meters. Okay, because therefore you'd have enough extension with that. So when we did it in class, we used a 2 meter wire. How would you determine the cross-sectional area of the wire? So first you'd measure the diameter. You'd halve the diameter to figure out the radius. And then you would use pi r squared to figure out the cross-sectional area. And remember, you'd measure the diameter in different places to make sure it's uniform, and also you measure diameter using a micrometer. State the unit of K, the constant proportionality in Hooke's law. Okay, so we know this: F is equal to Kx. Okay, K therefore is equal to F over X. That's newtons over meters. That's newtons per meter. Okay. There we go, it's pretty straightforward, that one. Show that for a wire of length K, the cross-sectional area A, the Young's modulus is KL over A. Right, okay. So let me show you this step by step. K is equal to F over X. Okay, I've stated up over here that the Young's modulus is FA over XLO. So let's write that clearly. So Young's modulus is equal to, let's make this bigger. Young's modulus is equal to FA over XLO. Okay, X over LO, sorry. So what that actually ends up meaning in the end, well, LO is the length of the wire, so they've just got LO is L like that. Okay. So because I've got a divide of this, okay, I could do the reciprocal of this and multiply it by that. That's what a divide actually means. So that is the same as doing F over A multiplied by LO over X. So I've just done the reciprocal of this and multiplying it now instead of dividing. So I'm doing the reciprocal of this part over here, reciprocal. So in other words, the other way around, flipped it over, and now I'm multiplying it. So dividing by a value, or dividing by a fraction, is the same as multiplying by the reciprocal of that fraction. So if I now multiply that through, so I've written LO again, it's just L they want. So that's going to end up being F times by L on the top, divided by A times by X. Well, F over X we know is equal to K. We know that from before. So surely you can just replace the F over X by K, and you can't. You end up with L over A. Kx over A is exactly what they want. Nice 3 marks. And that brings us to the end of task 3. Let's just double check the mark scheme to check that we're doing the right sort of things. Just an normal cross-section area. Property gold malleable or ductile. Brilliant, nice, straightforward. Hard material, not easily scratched. Stretched, remain stretched when deformed, or deformed when the force is removed. Okay, so firmly fixed to a ceiling, beam or bench. So we would fix it to a bench. We've got a load, we've got a ruler and a scale, we've got a means of measuring small extensions. So we've got a pointer or a vernier scale. Alright, now we didn't do that, but I've mentioned this in the past. They need a pointer on here so you can measure. So you need a pointer on here so you can measure a very small movement. Damn it, forgot about that one. Okay, so it's called a fidual marker. That's a technical phrase for a fidual marker. Okay, or could you say a pointer that allows you to measure a very small scale. Okay, so wire being tested needs to be greater than 2 meters, greater than or equal to 2 meters. So micrometer, diameter in several places, just like we said. Newtons per meter is fine, just like we said for that one. And that's exactly the method that we use to do that one too. That's the end of the video for task 3. That leaves 2 more tasks to complete in unit 1 materials. Thank you very much for listening, guys.